So this is our presentation on arc length, a topic covered in the AP Calculus BC exam. A note for our teacher, Mr. Krause. Any graininess in equations are actually because we use screenshots to preserve the formatting from a Google Docs, which has been provided at the end of this presentation for your reference. So let's begin. So these are the equations for arc length. Length equals integral a to b square root of 1 plus dy over dx squared dx, or length equals integral a to b square root of 1 plus dx over dy squared dy. The first equation you see is for equations you see in the form y equals something x, and for the second one in the form x equals something y. So where did we get this equation from? Let's start with a triangle with side lengths x, y, and l. Now imagining the triangle as infinitesimally small along a function, dl represents the arc length, but as dl gets smaller and smaller, it's no longer an approximation of the arc length, but the actual arc length. Now by Pythagorean's theorem, you know that dl squared equals dx squared plus dy squared. Now we're simply going to factor out dx squared on the right side, and then divide both sides of the equation by dx squared, which gives you the dl over dx squared on the left. Now we take the square root of both sides, getting dl over dx equals the square root of 1 plus dy over dx squared. Now we're going to multiply both sides by dx, getting dl equals the square root of 1 plus dy over dx squared times dx. Now we simply integrate this formula, getting the integral between a and b, square root of 1 plus dy over dx squared dx equals the arc length. So the problem asks us to find the length of the curve y equals the natural log of x minus x squared over 8 for values of x between 1 and 4. So the first thing, our formula of the arc length is length equals the integral between a and b of the square root of 1 plus the derivative of the function squared dy or dx. So first we need to find the derivative of the function. So that would give us y prime equals 1 over x minus x over 4. The next thing we need to do is figure out what 1 plus y prime squared is equal to, since that's a function we need to kind of create. So that would give us, if you did 1 plus the derivative squared, that would give us the quantity 1 over x plus x over 4 squared. You can see the math that we did in order to achieve that final expression. So now we can put everything into the equation, right? So that gives us the length, the arc length, is equal to the integral between 1 and 4 of the square root of the quantity 1 over x plus x over 4 squared dx. So if you just do some basic integration in math, you end with the answer of the natural log of 4 plus 15 over 8. So the next problem asks us to find the length of the curve of the function x equals 4 times the quantity times the quantity y plus 3 squared, values of y between 1 and 4. So we approach this problem the same way we did the first one, except for the fact that the function is in terms of y instead of in terms of x. So the first thing we did was to find what the value of 1 plus the derivative of x squared was equal to, just like we did in the first problem. And that we found to be 1 plus 64 times the quantity 3 plus y squared. So now we put this into our formula of the arc length equals the integral between a and b of the square root of 1 plus the derivative squared, dy or dx. So in this case, the arc length is going to equal the integral between 1 and 4 of the square root of 1 plus 64 times the quantity 3 plus y squared dy, since it's in terms of y instead of in terms of x. And you can just use your calculator to figure out the answer to this question, which will give you 130.957. So for our third problem, we're going to find the arc length of y equals x to the third divided by 6 plus 1 over 2x on the interval 1/2 to 2. So just like before, we're going to find the derivative of the function using simple differentiation. This gets us y prime equals x squared over 2 minus 1 over 2x squared. And then we also factored out a 1/2 for convenience, which you don't really have to do, but it's just something that might make integrating later easier. And then, yeah, that gets you y prime equals 1/2 times the quantity x squared minus 1 over x squared. So now you can, again, plug in this derivative into your arc length equation, which gets you L equals, from the integral of 1/2 to 2, square root of 1 plus quantity 1/2 quantity x squared minus 1 over x squared, and all of that squared dx. And then you can, again, plug that into your calculator if you have a calculator, and if you don't, you expand it or do whatever you can with integration to get the answer, and you get 33 over 16. So from these three examples that we just did, you should be able to see that arc length is a relatively simple topic. We mostly emphasize the setting up of arc length by putting it in the arc length equation, which is the most important thing you should take away from this video. The integration is stuff you've already been doing in calculus. So normally arc length is relatively simple. The hardest part is actually just integrating. If you have a calculator, you're set, but if you don't, here's a reminder of common integration techniques. Use substitution, integration by parts, reverse chain rule, trig substitution, and partial fraction decomposition. You can find a review of these methods from other students in Mr. Krause's class. But you do have to be careful when doing arc length problems. There could be a vertical, tangent, corner, or cusp in the interval of the integral you are taking, and dy over dx will be undefined. So what should you do with this type of problem? For a vertical tangent problem, for example with the equation y equals x to the 1/3, you simply change the equation in terms of x, getting x equals y to the 3rd. Now you can solve with dx over dy instead of dy over dx, which would have given you undefined. For a corner, which you can easily tell if the equation has absolute value, you simply split the curve at the corner, which is commonly at x equals 0, and then write the function without the absolute value, so split it into two equations. So basically, you split the curve and then you add the separate arc lengths. Arc length in real life. Is arc length actually applicable to real life? You might ask. Yes. Arc length is found anywhere where there are arcs, and you would want to know how long they are, for example, in curved windows, and in a lot of modern architecture now that all have curves. If you wanted to, for fun, find the curve of the Eiffel Tower, you could do that. And also in art, you find a lot of arcs that you could find the length of. And also in art, there is not just arc length, but also many other forms of calculus. If you wanted to give a present to your math teacher, you could even make him a piece of art and then calculate the arc length, and then he would be like, wow, that's a great present. Yeah. So that's the end of this video. Thanks for watching. Here's the Google Doc that we talked about earlier, in case you want to see any problems up close. Look out for our other video which explains area between curves and also volume by cross-section.